It's my pleasure to introduce Daniel Berlyne from University of Bristol. He's going to talk about braid groups and cube complexes.
Thank you very much. Thanks for the invitation. It's a pleasure to be speaking here today. So I'm going to be talking about braid groups and specifically braid groups of graphs and how they decompose as graphs of groups. And along the way, I'm going to be using some cube complex machinery. So I'm going to start off just by going through some of the background on cube complexes and how this is going to be used in the graph of groups decompositions. So first of all, when I say an n cube, I mean the direct product of n copies of the unit interval with the standard Euclidean metric. And then, so for example, here's a 3 cube. Then a mid cube is obtained by restricting one coordinate to 0. So literally just take a cross section through the middle of one of the sides of the cube. Then a cube complex is obtained by gluing cubes of different dimensions to each other along subcomplexes. Okay, so we're considering these cubes as CW complexes, I should say. Okay, so for example, we might have something that looks like this. You can see we've got some 2 cubes here. And this triangle here consists of 3 1 cubes glued together. And then some of these 2 cubes, you'll notice appear to be kind of stretched and bent, but these are all supposed to be unit squares. They just appear a bit stretched just to make it easier to draw. So this here, don't know how easy it is to see, but this is supposed to be a torus constructed from squares, and then these 2 are also tori. Okay, so that's an example of a cube complex. We also have the notion of a hyperplane in our cube complex, which is obtained by taking a mid-cube and then extending it through the cube complex. So what I mean by this is consider some mid-cube, say this one, and then this mid-cube meets the 2 cube below it along its boundary. So we can extend it through that 2 cube by adding on another mid-cube. And then we can continue doing this. So now we can attach on that mid-cube and then also the mid-cube of this square that bends around the back. And then finally, we can add on this mid-cube here. And at this point, there's nowhere left for us to extend the hyperplane. So this blue thing is a hyperplane of our cube complex. We also have a notion of a combinatorial hyperplane, which is exactly the same, except when constructing the mid-cubes, you restrict to plus or minus a half instead of 0. So in this example here, we get 2 isometric copies of our hyperplane corresponding to restricting to plus or minus a half. And the advantage of these is that they give you copies of the hyperplane that are actually subcomplexes of your cube complex. Right. We also have a notion of non-positive curvature in a cube complex. And I'm going to give you kind of a somewhat informal definition, but hopefully this gives you an idea of what's going on. So we say the cube complex is non-positively curved if whenever you have three squares around a single vertex, and this also applies to higher dimensions, that implies that you actually have an entire 3 cube there. So any 3 squares form the corner of, any 3 squares around a single vertex form the corner of a 3 cube. And then also, we aren't allowed to have 2 squares glued together along 2 consecutive edges. Okay. So, right, so given this non-positive curvature, we can also define what it means for a cube complex to be special, which is a stronger condition, which consists of the non-positive curvature condition plus some conditions on the hyperplanes. So the first condition is that the open half neighborhood of a hyperplane is homeomorphic to the hyperplane across the open unit interval. So in other words, the hyperplanes don't run through Mobius bands. Second condition is that hyperplanes do not self-intersect. Okay, so it should hopefully be clear what that one means. Thirdly, hyperplanes do not self-osculate. And that's what this first picture on the right is illustrating. So in other words, when you take the closed half neighborhood of the hyperplane, it doesn't have this kind of self-tangency. And then finally, hyperplanes do not interosculate. And that's illustrated by that second picture on the right. So if you have 2 hyperplanes, they can't both intersect and then later on osculate with each other. And these conditions give some nice geometric and algebraic properties to cube complexes and their fundamental groups, which have proven very powerful. For example, Haglund and Wise use special cube complexes to prove Thurston's virtual Harkin conjecture for 3 manifolds. And we're not going to be thinking about 3 manifolds today, but that's just one example. Another example is that special cube complexes can be decomposed as graphs of groups quite nicely by cutting along hypergroups. Or I suppose the cube complex can be decomposed as a graph of spaces, and its fundamental group as a graph of groups. And because of these nice properties to do with self-intersection and so forth, when you cut along the hyperplanes, it does split up the cube complex in a nice way. Okay, so right, so here's an example of one of these decompositions. So this is a slightly more complicated version of the cube complex that we saw just before. So again, we can choose a hyperplane, which this time is going to include the mid-cube running all the way around here, and this guy here. So these, again, these elongated squares are really supposed to be unit squares. They've just kind of been stretched and twisted around. Oops, I did the wrong one there. But anyway, they've just been kind of stretched and twisted around, so it's easier to draw. Okay, so we cut along this guy, and then we get this cube complex here. Let's call our hyperplane XE, and this space on the right XV. So we can now reconstruct the cube complex X from these simpler cube complexes XV and XE. And we do this through a graph of spaces. So let's take our XV, and then what we've done when we've cut along XE is we've removed the open half neighborhood of the hyperplane. So if we were to try and recover our space X, we would take XE cross an open half neighborhood and then glue it to XV by, well, in the case of the cube complex, by gluing along the combinatorial hyperplanes. So here, even though we don't have the hyperplane XE anymore, we can still see these combinatorial hyperplanes. In XV. Okay, so we can represent this data with a graph. In this case, we're going to have a single vertex V and a single edge E, corresponding to the space XV and the hyperplane XE. And then we also have two monomorphisms, phi E plus and phi E minus. And these are simply the embeddings of the two combinatorial hyperplanes. Into XV. Okay, so all of this together, this data gives us a graph of spaces, decomposition, or alternatively, if we look at the fundamental groups, we get a graph of groups. So this tells us that pi1 of X is isomorphic to pi1 of XV, and then we take an H&N extension over pi1 of XE. Okay. And again, we're identifying two copies of pi1 of XE, which appear as the two combinatorial hyperplanes. All right, so so the advantage of this is that we are able to compute the fundamental group of our cube complex by computing the fundamental groups of these a priori simpler spaces. The fundamental group of XE is, of course, just going to be Z, since it's just this single loop here with some edges coming off it. And then XV is a little more complicated, but what we can do is we can rearrange the pieces, and it actually becomes this space Y. So maybe let's get rid of these orange bits. Oops, and it might become a bit clearer. I think that's good enough. Okay, so right. So maybe it's clearer if I highlight the various pieces. So this piece here in in XV is this piece here in Y. And then we are kind of contracting these squares here so that this piece swings around underneath. So this piece here swings around to this piece here. And then similarly, if we contract this square here, then the triangle at the top becomes this triangle at the side. Okay, so we end up with this space Y, which is much easier to compute the fundamental group of. It certainly seems much simpler to look at. And in fact, we can continue decomposing by cutting along hyperplanes to make our computation even easier. So we can cut along this hyperplane YE. And this time, we end up with two connected components when we cut along this. Let's call these connected components YU and YW. So in the graph of spaces decomposition, we have two vertices U and W, and again, a single edge E. And once again, we have two monomorphisms corresponding to the embeddings of the two combinatorial hyperplanes, one in YU and one in YW. And in fact, we can continue and decompose YW even further by cutting along this purple hyperplane, and so on and so forth. So in this case, fundamental group of Y is the fundamental group of YU amalgamated over fundamental group of YE with the fundamental group of YW. And right. And if we give names to all of these generators, we can actually write out explicitly what this group is. So let's call this 1A. This loop gives a generator B. And then let's call the purple one C. Then we also have D. Then fundamental group of Y is going to be the Z squared generated by the A and B that form the torus on the top, amalgamated over the Z generated by the B with the Z squared generated by BC, amalgamated over C with the Z squared generated by C and D. And then finally, we have a copy of F3 corresponding to these three triangles. Okay, and then we can plug this into the fundamental group of X. And we will get the same thing with an HNN extension. So we add an extra generator. Let's call this one T. And then add in a relation, which is going to be D inverse TA T inverse. Right, and you can see this by going back and looking at what you're actually gluing in XV. We're gluing this guy here to this guy here. Well, we're gluing along the whole hyperplane, but those are the two loops that we're gluing to each other. And the red guy, if you look back at Y, that's this guy, which is the A generator. And then this blue guy is this guy, since we swung this piece down and around, and that's the D generator. Okay, great. So we've seen that this somewhat complicated cube complex can be decomposed, and we can actually compute quite explicitly what its fundamental group is. And we're going to bring this technology to braid groups. So, right, so let's define a braid group first of all. So we're going to start with a topological space, any topological space, and then the configuration space is going to track the motion of n particles as they move around X. Okay, so imagine you have this space X, and you've got some number of particles moving around, weaving in and out of each other. Okay, without colliding, I should emphasize that. Okay, so the idea of the configuration space is, well, it's going to be the space of all the possible configurations. So we start by taking a direct product of n copies of X, and these are going to represent the locations of the n different particles. And then, because the particles aren't allowed to collide with each other, we remove a diagonal consisting of all of the n tuples, such that xi equals xj for some I not equal to j. Okay, so right, in other words, no two particles can occupy the same location. And then finally, notice that actually we have implicitly been labeling our particles, because since we're representing them with an ordered n tuple, we're implicitly labeling them 1 through n. But in reality, we generally do not want to distinguish between the different particles in this way. So usually we will consider the unordered configuration space, which is just the configuration space, but we take the quotient by the action of the symmetric group by permutation of the coordinates. Then the braid group is just the fundamental group of this. And we may need a base point in our fundamental group. We haven't made any assumptions about X. So in particular, X could be disconnected. And in fact, it turns out that the unordered configuration space is connected if and only if X is connected. And in fact, the number of connected components of our configuration space is precisely the number of ways to partition the n particles among the connected components of X. So you can think of S as being an initial configuration of the particles. And then once the particles have been placed in their various connected components, they're kind of trapped in these components. They can move around them, but never out of them. And so that gives you different connected components of the configuration space. Okay, right, so one classical example of a braid group is when X is the disk, and this gives you the classical braid group. I'm not going to go into why this is the classical braid group, just because it's a bit off topic, since we're going to be focusing on graph braid groups. But I'm happy to explain why that is the classical braid group at the end, if anyone's interested. But right, like I said, we're going to be taking X to be a finite graph. So some collection of vertices connected by edges. And the reason that we're doing this is because there is this very nice theorem due to Abrams and improved upon by Prue and Scrimshaw and also Crisp and Wiest, which tells us that the unordered configuration space of a finite graph deformation retracts onto a special cube complex. And there is a small caveat here. The deformation retracts if and only if the graph gamma satisfies the following two conditions. So first of all, every cycle in gamma has length at least n plus 1. And secondly, every path in gamma between vertices of valence not equal to 2 has length at least n minus 1. Okay, now these two conditions here are somewhat artificial because you'll notice that the definition of the braid group is a purely topological one. It only depends on the topology of this graph gamma. So in particular, if we add extra valence 2 vertices, this does not affect the braid group at all, since these are indistinguishable from any points on the interior of an edge. So what we can do is we can just keep on adding valence 2 vertices until the conditions of the theorem are satisfied. So the upshot of this is that any graph braid group is the fundamental group of a special cube complex. Okay, so we're going to denote our special cube complex by UCN of gamma. So this is also called the combinatorial configuration space. This is no longer a purely topological object because we do require we do care about the valence 2 vertices now, but we can always arrange so that gamma satisfies these conditions, and then we have the deformation retraction onto this cube complex. Okay, great. So now we're able to apply our graph of groups decomposition tools. But first of all, we need to understand a bit better what this cube complex actually looks like. So let's take a look at an explicit example. So we're going to take this graph that we had from before, and we're going to look at the configuration space on 2 particles, just to keep it simple. So if we go back to the definition of the configuration space, first of all, what we did was we took the direct products of n copies of our space, and we removed a diagonal, and then we quotiented by the action of the symmetric group. So if we try doing this with gamma, well, if you take a direct product of 2 copies of gamma, then this is quite clearly going to be a cube complex. You get a cube when you take a direct product of some number of edges, and and so the direct product of graphs is going to be a bunch of cubes glued together along subcomplexes. But the issue is when you remove the diagonal. That is going to break some of the cubes. I mean, for example, if you take a square and then remove the diagonal from that square, That's then going to give you two triangles. And then the deformation retraction is what's going to save us here by retracting this so that you get rid of those kind of partial cubes. Okay, so right, so in practice, how do we draw this cube complex? Well, first of all, let's look at the vertex set. We have 9 vertices in our graph, so we get a 9 by 9 grid of vertices. And in fact, it's going to make our lives easier if we label these vertices just to make it easier to keep track of what the vertices of the cube complex represent in terms of the graph. So then we remove a diagonal. And then we quotient by the action of the symmetric group. And effectively, this means we're just going to look at the lower triangle here. So this gives us the vertex set of our cube complex. Now the edges, we're going to need to really look at what the vertices correspond to in the graph to determine what the edges are. So let's say we take this 1, 3 vertex in the configuration space. This corresponds to taking the 1 vertex of gamma in one copy of gamma and the 3 vertex in the second copy of gamma. So this is going to correspond to having a particle sitting on the 1 vertex and another particle sitting on the 3 vertex. Then we can see that this particle at the 1 vertex can move around to the 2 vertex unobstructed. So that tells us there is an edge in the cube complex from the 1, 3 vertex to the 2, 3 vertex. Right? Because we see this entire 1, 2 edge across the 3 vertex. Similarly, the second particle can move unobstructed to the 4 vertex. So we get the 1, 3 vertex is connected to the 1, 4 vertex. And then in fact, these two red edges, closed edges, are entirely disjoint from each other. So when we remove the diagonal, we do not remove any of the product of those two edges. So we get an entire square here. And we can keep doing this for the whole cube complex. In fact, Anthony Gervois has a nice description of this process. So the vertices, as I mentioned, are the configurations of the particles on the vertices of gamma. Then 2 vertices of the configuration space are connected by an edge, if and only if the corresponding configurations differ by moving a particle along a single edge of gamma. And in fact, this means that we can always label edges of UCN of gamma with edges of gamma. And then finally, M edges span an M cube if and only if their labels are disjoint. So, right, so we can apply this construction and obtain the following cube complex for UC2 of gamma. So as you'll notice, this is exactly the cube complex that we computed the graph braid group thought before. So recall that we were decomposing along this blue hyperplane. And when we cut along this hyperplane, we got this cube complex down here. Now, you might notice that the edges that this hyperplane intersects are precisely the edges labeled by the 3,4 edge of gamma. In fact, this blue hyperplane intersects all of the edges that are labeled by the 3,4 edge of gamma. And what we've done when we've cut along this hyperplane is we've removed all of these edges. So in fact, what we get is the configuration space of the graph gamma minus the open 3,4 edge. So we end up with the configuration space of lambda. So actually, when we computed the graph of groups decomposition, we were expressing the braid group B2 of gamma as an H&N extension of B2 of lambda. And my main theorem is saying that this is a general construction that you can do for all graph braid groups. So if you take M edges, gamma, that share a common vertex. Then Bn of gamma. Now, notice that we're not using the base point notation. We're dropping the S because in general, we're going to assume that gamma is connected just for the sake of simplicity. Right, so then Bn of gamma decomposes as a graph of groups. With vertex groups, let's denote these by GV. The vertex groups are precisely the braid groups Bn of gamma minus the union of the open edges, E1 through En. And here we actually do need to specify a base point S in general, because removing these open edges might disconnect our graph gamma. And in fact, the vertices of the graph of groups are precisely all of the different possible graph braid groups that you get by choosing different base points. So the number of vertices of your graph of groups is going to be the number of partitions of the n particles among the connected components of gamma minus the open edges. And moreover, we also know what the edge groups are. These are going to be the braid groups on n-1 particles of gamma minus the closed edge EI with a base point SI. Okay. Again, removing the closed edge might disconnect the graph, so this base point does matter. And in fact, the full theorem is a bit more detailed than this. We actually also know precisely which vertices are connected by edges and how many edges there are between two vertices. But that gets very technical, so I'm not gonna go into that. Right, and in fact, we saw just before why our vertex groups are these braid groups on gamma minus the open edges. So as a proof, I'm just going to give a heuristic for why the the edge groups look like this. And really, it just comes down to what the combinatorial hyperplanes are as configuration spaces. So if we look at one hyperplane that's labeled by an edge EI, recall that the hyperplanes run through edges that are labeled by a particular edge of the graph gamma, so we can label the hyperplane by an edge. So if a hyperplane is labeled by EI, the two combinatorial hyperplanes correspond to fixing one particle at one of the two vertices of EI, and letting the remaining n-1 vertices move around gamma minus EI. Okay, so that's why we end up with the Braid group on n-1 particles for the edge groups. And if we look up at the example again, we can see this happening here. So if we take this combinatorial hyperplane here, we can see that this corresponds to fixing one particle at the three vertex, and then letting the other particle travel along the other axis of this grid, and travel in particular along the vertices, through the vertices labeled 5 to 9, and then also once it comes around to the top bit here, we're still fixing the 3 vertex and then letting the particle move along the 1 and 2 vertices. So what we get is the Braid group on this red subgraph with just one particle, since the other particle is being fixed at the 3 vertex. And the Braid group on one particle is just going to be the fundamental group of the graph, since we don't have a diagonal to remove. And that is just going to be Z, since this red subgraph just has a single loop. Great. Right, and we saw that indeed the edge group in the example we computed was a Z edge group. That's what we were amalgamating along. Okay, so we also have some nice corollaries that we can derive from this theorem. So for example, we can obtain some criteria for a graph Braid group to split as a free product. Okay, so if gamma contains an edge E such that gamma minus the open edge is connected, but gamma minus the closed edge is disconnected, and one of the components of gamma minus E is a segment, so just a straight line segment, then Bn of gamma splits as a non-trivial free product. So this can be seen in the example from before. We can choose this edge, for example, then the open edge does not disconnect the graph, but the closed edge does. And the way we obtain this free product splitting is by noticing that, well, first of all, the open edge doesn't disconnect the graph. So we have a single vertex in our graph of groups decomposition. Since we only have, since the choice of base point doesn't matter if the graph is connected. And then the closed edge does disconnect the graph. So the edge group, well, we're going to have multiple edge groups corresponding to the different partitions of the particles among the two connected components of the graph. But notice that one of these partitions is going to consist of putting all of the particles in the segment component. And so by trapping them in this segment component, we end up with an edge group that is just the trivial group. The braid group of a line segment is trivial. So this means that our braid group has a free Z factor corresponding to this loop with the trivial group associated to it. We also obtain another similar theorem for different kinds of graphs. So also if gamma can be expressed as a non-segment flower graph phi with a connected non-segment graph omega glued to its central vertex. Then again, Bn of gamma splits as a free product. So here, when I say a flower graph, this just means a graph that consists of one single central vertex with a bunch of loops, a bunch of cycles and edges glued to it. Okay, so it might look something like this. And then we just have some other graph omega attached to that central vertex. Then if we take an edge with one of its vertices being the central vertex and the other vertex somewhere in omega, then we can decompose gamma as a graph of groups along this edge E. And again, we can play the same kind of game. We can trap all of the particles in phi. And when we remove the closed edge E, the flower graph phi just becomes a bunch of segments. So it's going to have trivial braid group again. So for similar reasons, we get a free product here. And in fact, I don't know of any graphs that give free products as the graph braid groups that don't satisfy one of these two conditions. So an interesting question would be whether there are actually other ways to get free products in graph braid groups. It would certainly be very very nice to have an if and only if condition here. Another interesting direction you could take this is by studying the relationship between a graph braid group and a right-angled Artin group. So another corollary is that if you have at least 5 particles, then actually a graph braid group is never isomorphic to a right-angled Artin group, assuming that gamma and lambda are both connected. So the right-angled Artin group, recall, is a group associated to a finite graph, a lambda here, where the generators of the group are given by the vertices of lambda, and then 2 generators commute if and only if there's an edge in the graph. So these are naturally related to graph braid groups. Every right-angled Artin group embeds in a graph braid group, and every graph braid group embeds in a right-angled Artin group. But interestingly, it seems that it's in general difficult to actually get an isomorphism between the two. So it'd be interesting to see whether such a result can be obtained for n less than 5 as well. But yeah, I think I'm going to finish there. So yeah, thank you very much.
Thank you very much, Dan, for a great talk. Are there any questions for Dan?